diffusion. Okay, oxidation, sorry. Oxidation. Is that right? No. Oxidation should be. Oxidation. Okay. And today we are going to talk about the oxidation induced stacking force. It's going to be called OISF. Okay, and then next lecture we're going to discuss about the oxidation enhanced diffusion, OED. Probably you may see the sequence is going to be a little bit changed, but we're going to follow this sections, okay? Last time we talked about the dopant enhanced diffusion, enhanced oxidation, and in there we have seen that when we talked about the dopant enhanced oxidation, we have seen that there are two constants in oxidation, in Deal and groove model. And here we have a parabolic rate constant and the B over A linear rate constant. And this linear rate constant is related to the surface reaction for the silicon and oxygen and then silicon oxide. This chemical reaction. And for this reaction, the vacancy of silicon plays an important role. So we have seen that especially in the phosphorus case, it has doubly negatively charged vacancies going to be dissociate into this manner, and under certain circumstances that we are going to have extra vacancies. So this extra vacancy is going to work on this reaction, so that when we plot the B over A with concentration of phosphorus, then up to 10 to the 19th, 5 times 10 to the 19th, the V over A is not changing much, but after this, it's exponentially increased, like this. So this is the reason why we have a enhanced oxidation with a dopant. And this happens particularly for the case where the phosphorus is used as a dopant. And on the other hand, the B, the parabolic rate constant, states constant values. That has been experimentally found. So we have a pretty much understanding. We have a pretty much understanding of dopant enhanced oxidation, and we try to explain that phenomenon in the light of the vacancy models. Right? Now, in the oxidation-induced stacking force, OISF case, we want to use a silicon interstitial model rather than silicon vacancies. Okay? So before go into the stacking OISF, I want to say something about the stacking. What is stacking? Stacking is a when you put the atoms, think atom is a ball, then the close-packed plane can be formed somewhat like this, and then if you want to make a 3D bulk solid, then you have to put something on top of this, okay, and then that we call the stacking. So when you build a solid bulk, the x and y, and then there is a g-axis, and then in the x and y plane, for the three-dimensional bulk construction, you have to put the atoms along the g-axis, and that is going to be called the stacking. Okay, so let's turn on this thing. When you talk about the stacking folds, there should be a there can be a fault in the stacking. Means when you put the atoms along the g-axis, we can have some faults in there, defects we should say. And those defects is related with the motion of the silicon, vacancies or silicon interstitials, whatever. So if you're a material scientist, you may be familiar with the stacking and crystal structure thing, but if you're not majoring in material science, probably the stacking folds and those terminologies may be difficult. The page is going to be. So there we go. Let me do this a little bit. So today we are going to talk about the oxidation induced stacking faults, OISF, and this is a little bit difficult to understand, but if you look into the material, the z-axis is the one direction, which means there is a normal to the 1, plane, and 1, is the closed packed structures. And stacking fault means we have an extra plane here. You know, normally the white balls are normal matrix of a silicon, and then if you have some extra plane in this directions, then it ends at here, and then it is kind of a plane located just like this. Okay, so when you talk about the stacking faults, we are talking about the growth and the shrinkage of this extra plane. So here's some explanation for that. Extrinsic stacking faults are formed by the introduction of additional layer of atoms. They are generally 2D structures. It's an extra plane lying on inclined one-on-one planes, closed planes, and bounded by partial dislocations. We call this dislocations, but you may understand this or not. It's not big matter. Anyway, the important thing here is the stacking fault growth in length by adding extra silicon atoms, which means observing silicon interstitial. Okay, so it has been deduced that the process conditions which grow OISF generate the silicon interstitial. A special silicon etchant may reveal the stacking faults here. This and this is the end of extra plane. The extra plane is supposed to be like this, and then when you use a special etchant, okay, these fault areas is going to be etched preferentially so that we can see directly the images like this. This is a TEM image, by the way. And silicon stacking faults can be nucleated by mechanical damage, impurity precipitates, crystal growth defects, implantation damage, and things like that. Of course, we are talking about the perfect single crystal, otherwise. Okay? And during thermal oxidation, stacking fault normally grows, and we want to understand why the stacking faults can grow. If you have a situation like a stacking fault growth, then it is not good news for you. We have some fault which is growing. Okay, so if you have a certain number of if your perfect single crystal silicon contains certain number of stacking faults, and you carry out the oxidation of a silicon, then these faults, stacking faults, will grow with the oxidation, and that is not good news. So we want to understand why it grows, and actually we want to prevent that. Okay? Experimentally, what we can see here is the oxidation time, and at different oxidation temperature, stacking faults length, as you can see, it grows. It's a log scale with the oxidation. And at this elevated temperature, it may deviate from the straight line, but generally it grows with the oxidation. And OISF length increases with the time of oxidation, and the growth rate is faster at high temperature, at least below 1200 degrees Celsius. You can see in the experimental data, right? And here's another plot, stacking fault length in the y-axis, and the oxidation time. And now in this experiment, we change the oxygen concentration in the oxidation. We change the environment, okay? And then as you can see, if we increase the oxidation, then it is going to enhance the stacking fault growth. So temperature and oxygen concentration in air will enhance the stacking fault growth. Here's another plot, and this is a logarithmic stacking fault length, and here's another oxygen concentration, and you can see the slope, the activation energy is almost the same no matter what the oxygen concentration, and it's about 2.3. And this 2.3 electron volt is very familiar with us, right? That is the silicon-silicon bonding energies. That is almost the same to the bonding energies. So what we can see in this plot is that the stacking fault growth is related to the silicon-silicon bonding. It's basically related to the breakage of the silicon-silicon bonding or attachment of the silicon to the dangling bonds already broken. All right? The activation energy, 2.3 electron volts, over a fairly wide range of thing. And this is the interesting experiment to notice. 1150 and 1220 and 1230 degrees centigrade. As we've seen before, under the temperature below temperature of 1200, it shows a straight line in terms of this plot, right? But when the temperature is beyond over 1200, then you see the retrogrowth of that, deviation from the straight line. And then if you increase the temperature just 10 degrees Celsius, 10 degrees, then you can see obvious retrogrowth of the stacking fault growth with respect to the time. So in this figure, at high temperature, OIS grow for a while and then begin to shrink as the oxidation continues. That's experimental results, and this is obvious. The length of OISF and then oxidation concentration, you can see generally when you go to the high temperature, this is the reciprocal. The x-axis is the reciprocal of the temperature. So if you go to the left-hand side of this figure, it means that we increase the temperature. And then the OISF, the stacking force grows with the time, and then it suddenly the growth has been stopped. And it decreases with the oxidation. So note, the temperature of retrogrowth decreases with the oxygen partial pressure decreases. And at temperatures beyond the 1200 degrees Celsius, rapid retrogrowth of OISF can be observed. How can you explain this? So we just set the model here. You have to, it's very interesting to notice how the theory has been developed to explain this phenomenon. The first what you have to do is you have just to set the simple equation. This is the growth rate of stacking fold, and it should have two terms because we have seen the retrogrowth at beyond the 1200 Celsius. So it should consist of two terms, and obviously the one is related to the growth of the stacking folds, and the other one should be related to the decrease in the stacking folds. And interstitial silicon should increase the stacking folds because the extra silicon atoms attaching to the bottom of the stacking fold will increase the stacking fold length. And in the same token, if you have a silicon vacancies attached to the bottom of the stacking folds, then the stacking fold length should be decreased by that amount. Okay, so this term is increasing the stacking fold, and this term is related to the shrinkage of the stacking folds. And the growth rate can be explained something like this. And then what we have to do is, what is K1 and what is K2? That's the thing we have to understand. Well, that's a hypothesis. Now, this term has some dx over dt is the oxidation rate, right? The x is the thickness of the oxide. And here the K2 we don't know, but it is something related to the shrinkage. And compared to the expression with the experimental data, we can see that n is about 0.4 here. So this is the growth rate, and since we have seen in the experiment that stacking fault grows with the oxidation, so it should be related to the oxidation rate, and then experimentally we can determine the value n here. And K1, we can determine this from the experiment, and the K2 also has been determined from the experiment. So we have this equation, and then we know this is the oxidative and growth model, the oxidation related thing. So we want to have a derivative with respect to the time of this equation, and then we end up with the b over 2x is such and such, and then we end up with this equation here. Okay? The 0.4 appears at here, and then the length, and then the length now is going to be related to the 0.88 power to the time, theoretically. And then here, the stacking fault length and the oxidation time. Again, this is the same, exact figure that we have seen a minute ago. Then neutral growth begins when that is the growth length, stacking growth rate, the derivative is going to be equal to 0, and that should be the maximum. Okay, so neutral growth begins when we have this situation. The derivative is going to be 0, and then you can have this is some misprint there, and then the neutral growth rate can be determined from this equation. First, the derivative of that. Okay, and then this simplified equation theory agrees well with the data. And that's a key thing. Okay, so basic model based on the silicon interstitial for the growth and the silicon vacancy for the retro growth seems to work. Okay. And n is equal to 0.4 from the experiment, and then from the oxidation equation, we end up with L is proportional to the time to the 0.8 power, right? And then that matches with the experiment pretty good. And activation energy of K2 neutral growth is turned out to be 4.8 electron volts experimentally. And this is close to the activation energy for silicon self-diffusion at high temperature. That's a pretty good approximations we have here. Okay, so in oxidation-induced stacking fault case, we start out with the simple equations. Okay. The way they develop theory is very important, and probably in your experiments you have the same situations. You have experimental data, and if you want to understand the basic mechanisms related with that, then the way you have to think is just like this. Now, experimentally, what we have seen here is that 1 over T, stacking fold length shows this kind of behavior, and then we set the whole governing equation, that is the stacking fold length. It should consist of two terms, and the one is the increasing the stacking fold, and one should be the decreasing stacking fold. And at this region, we have seen that the oxidation rate is related to the increase of the stacking folds, so that we want to set this one is related to the interstitial stacking, but it should be related to the oxidation rate, okay, and some nth power. And then here we know the oxidation rate from the Deal and Groove model, and then experimentally we have seen this is correlated to the 0.4, and this one is related to the T times the 0.2 power, so that as a total we have seen that this whole positive term should relate to the times the 0.8 power. Okay? And then experimentally it just matched, so we see that this model is okay, right? And for the decreasing part here, what we want to set is that the dt over dt, dl over dt is equal to 0 at the maximum, okay? So at here we see that this should be the 0, and then we can set this point from that equation. That's what we have seen here. So if you do the experiment and you have some competing parameters in there, then you can just set just like this, okay? And then one positive and negative, and then you have to apply the basic theories related with that, and then you end up with some equations, okay, just like this. And then you have to fit with the experimental data. You can just the fitting. You cannot just setting the equation which can fit the experimental data. It's very difficult. You have so many variables. You have to arrange. You have to screen some variables in some part. So the way you have to do is in your experiment, you just the process that we have developed in this class, you have to apply this method to your experiments. Okay, it's pretty nice, isn't it? Okay, do you have time for the oxidation enhanced diffusion? What time is it? Can you pull up the blinder so that we can see the time? 11:30. So we have to talk, now let's move to the next section, which is the oxidation enhanced diffusion. Okay. This is the reference, and here the oxidation can enhance the diffusion. Use phosphorus concentration, and this is the, I think this is the time. And then you see with the oxidation, the profile has been, diffusion has to be enhanced. And we can see both of the effects on both terms. This is the silicon oxide, and this is the silicon nitride. So Before the oxidation, the silicon surface, part of the silicon surface is covered with the silicon nitride so that the oxidation cannot happen. And then we have a certain phosphorus concentration here, uniformly doped on the silicon. And then if you carry out the oxidation, that underneath the silicon oxide, the delta X should be the enhanced diffusion induced by the oxidation process. And the mechanism which has been used to explain this effect is the generation of silicon interstitial at the silicon-silicon oxide interface during oxidation. We have seen this for the oxidation case before, right? OISF and OED are closely related. Now, how can you explain this? Interstitial silicon can enhance the diffusion, and that is one model. But you can think it just say that the interstitial silicon will kick the impurities at the substitutional site to the interstitial site. Okay, just to kick the normal site to the interstitial, and this interstitial is impurities can react with the silicon vacancies more, I should say, efficiently. Okay. In other words, the impurities in the substitutional site and impurities in the interstitial site, comparing these two impurities, the impurities in the interstitial site may have more chance to be coupled with the vacancies of silicon, so that the diffusion, actually, the impurities can move faster in this fashion. Okay. So we set up the equation. The increase in the interstitial silicon rate is related to these two terms, and it has the precipitation something which decrease the generation of interstitial. Okay. Again, we have two terms here. This is the fixed first law. Fixed second law. The diffusion flux due to the concentration gradient, and this is the chance for the recombination and the thermal equilibrium concentration and silicon concentration at interstitials, and this difference is going to be the driving force, okay, to meet the silicon interstitial with the silicon vacancies. So if you look at this equation carefully, you can see that this is the vacancies and this is the silicon interstitial extra from the thermal equilibrium values. So this times this means it has a chance for silicon interstitials to be recombined with the vacancies so that annihilate the silicon interstitials, right? That is just a probability statistics. So this is the generation rate, and this is the recombination rate, and this is somewhat we don't know. That's a precipitation of silicon interstitials somehow. So it is inactive silicon interstitial. So this equation looks complicated, but it just says the simple phenomenon: generation, recombination, and something which is the sink. Okay. So the second term physically represents silicon vacancy and silicon interstitial recombination. The third term, silicon interstitial precipitations. Of course. So under steady state conditions, the generation of silicon interstitials generation rate should be 0. That is the definition of a steady state. And for the time being, just neglect the precipitation thing. Then we can find the solution here, which can be represented as 31, equation 31. And here the thermal equilibrium values. And you can see the new parameters is LD, the effective diffusion length. That is when you say effective here, it just means that we don't know. We have to determine that in the experiment. Experimentally, it has to be determined, something like that. So we just dump it as effective diffusion length. Now, since the enhancement of diffusion coefficient should be related to the interstitial silicon, here the delta D naught has to be defined as the equation 32. And this is the simple equations which it can be from the 31, where Di is the impurity diffusion coefficient via interstitial mechanisms. And we make assumptions just like we have done for OISF, which means the excess amount is the Di naught, the instantaneous enhancement of diffusion, and that enhancement is related to the oxidation rate. Because the topic is the oxidation may enhance the diffusion coefficient. So that enhancement of diffusion coefficient should be related to the silicon interstitials. And that is related to the oxidation rate. Somehow, we don't know the N, we don't know the K, but we just, this equation just to say the enhancement of the diffusion coefficient of the dopant by the oxidation should be related to the oxidation rate somehow. So we just set 33, that is just assume, we just speculate it should be something like this, and then experimentally we have to determine the parameters related to this. Okay, now this is the well-known thing. We have discussed this before, and if you make a derivative of that, then you end up with that, and then you put this part on this equation, and then delta D naught is the time average to enhance the diffusion coefficient. And you just different from here. The I is the not intrinsic, instantaneous thing. And then we make an integral of that. You have a time average the values. And using the above equation and n equal to 0.4, it's just similar to the OISF case. And then we have equations which can be seen here. For an oxidation of duration time t, delta D naught enhancement in the diffusion coefficient can be given with the above equations. And then this is the rough plot, this is the x-axis, and according to that equation, 32, then we have B over A dominated region, where in the initial stage of the oxidation, right? And then later the probability rate dominated the case. We have 0.4 power relations of the diffusion enhancement data there. And the total diffusion coefficient is thus given by this, and we have instantaneous diffusion coefficient is related with this, okay? And then from you have to match that with the experimental data, and then for the boron case, the delta D naught has been plotted here, and then you see the lines, dotted line, and this is experimental data. They are pretty much in the on the line, okay. And depth dependence of delta D naught for phosphorus is pretty much matching there. And experimental measurement for the LD. So, you see, this is the silicon nitride, so that right here there's no oxidation, and then right beneath the silicon surface without any oxidation, you have increased the diffusion by the heat treatment this much. But when you have oxidation with the same heat treatment, you have very deepened the junctions like A. So obviously we can see that this oxidation will enhance the diffusion of this dopant, right? So delta Xj should be the A minus B, and that is the enhancement induced by the oxidation, right? And then that has been plotted here. And then it just said that the experimental data is pretty much matching with the equations that we have set up here. Boron, and then this is the compensation thing, okay. Diffusion coefficient versus total amount of impurities for boron and phosphorus diffusion. And then you can see the in the boron case, the dotted line, and the phosphorus case, it's a straight line, is something like that. Okay, there. And this is the when the silicon nitride is covered, one part, no oxidation and intrinsic oxidation and enhanced oxidation. So when you dope something, then oxidation rate, we have seen that oxidation rate is enhanced. That is the number one case we have discussed. Dopant induced dopant enhanced oxidation, right? So when firstly, the way you should look at this is, now this is the silicon and this is the silicon nitride, okay? And then you partly covered this part for the doping. So the phosphorus is doped. This is the doped area. Okay, after doping, you just remove this, and then you put the whole thing into the oxidation chamber. Then what's going to happen is that this one is not going to be oxidized at all, and this one we have intrinsic oxidation, and here we have dopant enhanced oxidation. Okay, so if you look into the oxide thickness, there is no oxide is going to form here, and then here we have certain oxidation, something like this. But here, this dopant will enhance the oxidation so that we have bigger oxide, something like this. This is the silicon oxide. It's going to be formed something like that. Okay? And then we have at this part oxide enhanced diffusion here. And then at this part we have a multiple doping and oxidation enhanced diffusions at this part. So this is this put everything in here. Okay, what's going to happen in the experiments? This is the models that we have developed in the interstitial part. Maybe this one is just my handwriting, which is not going to be there. But this is just to explain that if you have antimony instead of arsenic or phosphorus, boron, the antimony is the substitutional diffusion. It's not interstitial diffusion related thing. So in this case, you have decreased. Everything should be in the other way around. Oxidation will decrease the diffusion, and oxidation will decrease the stacking force and things. So just we have a different situation with the antimony. So that's what this graph is about, but you don't have to really want to know about this. You can refer to the references if you are interested in. But I just want to tell you that if you have antimony, that is different from the normal dopant species that we have discussed. Okay? So this is pretty much the oxidation-related topics. And then at the beginning of this class, I told you we have dopant-enhanced diffusion and oxidation-induced stacking faults and oxidation-enhanced diffusion, OED. Okay, we have discussed the three terms here. Now, next week on Monday, we're going to discuss about the implantation and the crystal structure recovery, the gathering. And then there will wrap up the fabrication processes for the micron-sized devices. Okay, and then after that, we're going to see the electrical properties, which can be, which has to be thought when you have a miniaturized devices. Okay. Okay. Have a nice weekend, and I'll see you on next Monday.